Welcome to Telli Bear's Techy Tidbits, lovingly hosted by AI. We're so thrilled you're joining our cozy corner of the internet today for another explainer.
Oh, me too. Today we're bringing you a fascinating needle-felt-styled scientific mystery. We're going to explore something that literally touches all of our lives, blending a microscopic puzzle with some of the most cutting-edge supercomputers on the planet. So grab a warm cup of tea and let's unravel this whole thing together.
To kick things off, let's talk about a super common misconception. You've probably walked down the cleaning aisle at the grocery store, right? And you've seen dozens of products, bleach, antibacterial wipes, boldly claiming they kill 99.9% of bacteria.
Right, exactly. And it makes you think, well, problem solved. If we can wipe out bacteria that easily, why are scientists so worried? But the truth is, the challenge we're actually facing, it isn't about cleaning our kitchen counters. It's a completely different kind of puzzle.
See, surface disinfectants use brute chemical force to just obliterate bacteria on countertops or doorknobs. It's highly effective, but it's totally toxic. You obviously cannot use bleach to cure an infection inside a human being.
Right, exactly. When we talk about antimicrobial resistance, or AMR for short, we're talking about bacteria living inside the incredibly delicate ecosystem of a human body. Over time, these bacteria have evolved these amazing biological defenses to resist the safe, targeted medicines, our antibiotics, that we actually rely on to treat infections.
Chapter 1. The Superbug Puzzle.
Now, we really want to frame antimicrobial resistance not as some doomsday scenario, but as what it truly is, an absolute masterclass in evolution. Bacteria multiply incredibly fast, and through natural selection, the ones that randomly develop a resistance to our medicines, those are the ones that survive and multiply. They are tiny, brilliant survivalists.
They really are, and they have this wild trick called horizontal gene transfer. So bacteria don't just pass their resistance down to their offspring, they can actually share resistance genes with completely different species of bacteria right next door to them.
Yeah, it's basically like tiny gamers passing around cheat codes to beat a really hard level. If one bacterium figures out how to produce an enzyme that destroys penicillin, it can literally just hand that cheat code over to its neighbor, which makes the resistance spread incredibly fast. Now, looking at this data from a major 2019 study published in The Lancet, you can really see the high regional burden of AMR globally. In 2019 alone, antimicrobial resistance caused 1.27 million direct deaths worldwide.
And it was associated with nearly 5 million deaths in total. So the stakes are undeniably high here, with lower respiratory infections being the most burdensome. This is a serious, urgent puzzle, which is exactly why the scientific community is just so laser-focused on finding new solutions.
Chapter 2. Why Discovery Stalled Out. So, if superbugs are such a massive puzzle, why did the discovery of new antibiotics slow down so dramatically after all the vibrant progress we saw up until the 1980s? It's a really great question. Historically, traditional discovery relied heavily on testing soil microbes and fermentation products. I mean, scientists literally found medical miracles just hiding in the dirt. But eventually, those easy biological discoveries just kind of ran out. Finding something completely novel that didn't just replicate what we already had, it became incredibly difficult, wildly expensive, and just so time-consuming.
And that leads right into the fire extinguisher economic problem. Developing a new class of antibiotics is estimated to cost around $2.6 billion. But unlike, say, a daily pill for blood pressure, a highly effective new antibiotic is put on a shelf and reserved strictly for absolute emergencies.
Exactly. You want to use them as little as humanly possible so the bacteria don't develop resistance to them. They are literally like a fire extinguisher, essential insurance that you hope to rarely ever use. But because of that, they don't generate high sales, which makes them a terrible traditional business model for pharmaceutical companies.
There's this quote that perfectly summarizes the whole complication. It goes, "We weren't running out of science. We were running out of search tools and incentive."
That is just so profoundly true. The scientific desire and the need, well, they were always there. But the old tools were simply too slow, and the market was completely broken. We desperately needed a new way to search, which beautifully sets the stage for the next phase of our explainer.
Chapter 3. AI Joins the Search. This is where the real hero of our modern story arrives, artificial intelligence. And hey, before you ask, no, the AI isn't dreaming of our cute little needle-felt dinosaurs with laser eyes. As fun as that would be. But the reality is actually even more amazing. The AI is essentially acting as a super-powered search engine. In the past, scientists had to manually synthesize and test compounds in a lab, one by one. It was a massive bottleneck.
But today, researchers can train a neural network to virtually screen more than 45 million chemical fragments in a matter of days. Days! The AI predicts which molecules might have antibacterial properties before a single physical test tube is ever touched. It completely bypasses that enormous manual bottleneck.
And the timeline of these recent breakthroughs is just breathtaking. Back in 2020, AI rediscovered a shelved diabetes drug called Halicin, recognizing it actually had powerful antibacterial properties. Then in 2023, AI helped identify apofursin, which targets a very specific dangerous bacteria without wiping out your healthy microbiome in the process.
Right, and by 2025, the leap was just staggering. We went from using AI to mine existing databases, to using generative AI to act as a molecular architect, literally designing completely novel compounds that have never existed before.
So the really crucial point here is this 2025 MIT breakthrough. By using generative algorithms, researchers designed over 36 million possible compounds completely from scratch. They synthesized a small subset of these AI-designed molecules and found they were highly lethal to superbugs responsible for drug-resistant gonorrhea and staph infections in lab mice. I mean, they are conjuring up molecular structures that are completely absent from any database, showing real-world antibacterial activity with totally novel mechanisms. It's incredible.
Chapter 4. Prove progress is possible. Now, we definitely want to stay very grounded here. Those amazing MIT AI discoveries we just talked about, they are still preclinical, so they aren't on pharmacy shelves just yet.
That's right, but the good news is we don't have to rely only on preclinical data to feel hopeful. In December 2025, the FDA actually approved 2 brand new oral antibiotics for gonorrhea: gepotidacin, branded as Bleach, and zoliflodacin, branded as Nuzolvence.
This represents the first new class of antibiotics for this priority infection in over 30 years. And the story behind zoliflodacin is just incredible. When the pharmaceutical giant AstraZeneca exited antibiotics research, a nonprofit called GARP actually stepped in to save and advance the drug. It absolutely proves progress is happening right now, even when traditional markets struggle.
So how did gepotidacin cross the finish line when so many others failed? Well, it succeeded through 3 key steps. First, it has a brilliant, novel mechanism that forces the bacteria to mutate in 2 separate places to resist it, which makes using those cheat codes we talked about much, much harder. Second, it relied on vital public funding, specifically from BARDA, to help offset those massive development costs. And third, it was driven by a collaboration with a major pharmaceutical company, GSK. It just goes to show that combining great science with the right financial support really does work.
Chapter 5. The Gap and the Hope. And that brings us to the final piece of our cozy puzzle, where we really have to balance the massive excitement of AI with the grounded reality of drug development. We have these amazing new tools, but there's a hurdle we still have to navigate carefully.
Yeah, we call this the stubborn gap, because even with AI dreaming up perfect new molecules in a matter of days, the rigorous process of bringing a drug from a digital concept all the way to a physical pharmacy, well, it still takes 10 to 15 years. Human clinical trials, safety testing, FDA approvals, they simply take time.
But despite that gap, we're definitely ending on grounded optimism today. The antibiotic pipeline is finally growing again. When the traditional market struggled, we saw nonprofits, governments, and dedicated researchers successfully stepping in to fund and advance these critical drugs.
Exactly. AI is accelerating the front end of discovery, public-private partnerships are funding the middle, and our understanding of bacterial resistance is deeper right now than it has ever been in human history. The puzzle is actively being solved.
So, if there's one thing you remember from all of this, let it be this. AI isn't going to instantly put magic pills on pharmacy shelves tomorrow. But it is fundamentally changing the search. It's giving our brilliant scientists the exact tools they need to stay one step ahead of the superbugs and, ultimately, to win. It really makes you wonder, you know? With these incredible supercomputers acting as our new search engines, what other medical mysteries will AI help us solve next? The possibilities are just truly inspiring.
They really are. Well, thank you so much for listening to Telli Bear's Techy Tidbits. I hope you have a magical day, stay curious, stay kind, and stay safe.